Today we are looking at statistical errors in serial dilution. So we'll start by looking at what statistical error is. Statistical error is the error that describes the difference between a value obtained from a data collection process and the true value for the population. And what we also have to notice that statistical error is always associated with accuracy. Thus, the larger the error, the lower the accuracy of your work. So now let's look at some terms. So we have accuracy, precision, and error. So when we talk of accuracy, the accuracy of a measurement is how close a result comes to the true value. And now let's look at precision. Precision is how repeatable a measurement is or how consistent results are when measurements is repeated. And error is the difference between the acquired value and the true value. And what we have to note is that whenever we talk of error, then it means there is a true value or result that is expected. So the difference between that true value and your calculated or the acquired value is what is termed as the error. So now let's look at serial dilution. So when we talk of serial dilution, is the stepwise dilution of a highly concentrated solution to a lower concentrated solution. And what you also have to notice is that serial dilutions are made by performing the same dilution multiple times using certain amount of previous solutions added to the subsequent solution. So from this diagram, we can see that we prepared a concentration of 0.0001 molar, which is a lower concentration, from our full strength wastewater of concentration 1.0 molar using a serial dilution. And to do this with the serial dilution, we first have to dilute our stock concentration, so which is 1 molar to 0.1 molar. Then later we dilute the 0.1 molar to 0.01, and from 0.01 to 0.001, and from the 0.001 to 0.0001 molar. So this is just an example of how a serial dilution is being done. Now, so to dilute the 1 molar stock to 0.1 molar solution over here, what you have to do is that we just have to pick 1 ml of our stock solution and add it to 9 ml of the ionized or distilled water to get this concentration over here. And also to get this concentration over here, so we also pick 1 ml of our 0.1 molar solution and add it to 9 ml of the ionized water or distilled water to get this concentration over here. And also to dilute this concentration to the 0.001 molar, we pick 1 ml of this solution over with this concentration and add it to 9 ml of the ionized or distilled water. And to prepare the final concentration, which is 0.0001 molar over here, we pick from the 0.01 molar a ml and add to 9 ml of the ionized or distilled water. And what we also have to notice that we have our dilution factors over here. So to prepare 0.1 molar from 1 molar, we have a dilution factor of 1/10, which is the same as 1 times 10 exponent negative 1 or 10 exponent negative 1. And also to prepare this from this, we have dilution factor of 1/100, which is the same as 1 times 10 to the negative 2. And to prepare this also, we have 1 times 1 divided by 1000, which is the same as 10 to the negative 3. And also to prepare this concentration from the stock, we have the dilution factor of 1 divided by 10,000, which is the same as 10 exponent negative 4. So now let's try our hands on some examples over here. So the first example is to prepare a lower concentration of 0.05 molar from our 10 molar stock solution over here in 10 mils final volume. So first of all, we are going to use the equation C1V1 equals C2V2. So from the example over here, we know our C1 to be the 10 molar, our C2 to be 0.05 molar, the V2 to be 10 mils, which is the final volume, and V1 to be the volume of the stock solution that will be needed to prepare the final concentration 0.05 in 10 mils. So what you have to do is to make V1 the subject. And making V1 the subject, we have V1 equals C2V2 all divided by C1. So if you have to substitute these values into the equation, we will have our V1 to be 0.05 mils. So what it means is that to prepare a lower concentration of 0.05 molar in 10 mils from the stock solution, which is the 10 molar, you will pipette 0.05 mils of your stock, which is the 10 molar solution, into a different beaker containing 9.95 mils of distilled water. So let's look at the second example, which I'll say is a two-step serial dilution. So in this example, we can see that we are supposed to prepare a lower concentration of 0.05 molar from the 10 molar stock solution by first diluting it to 5 molar before preparing the final volume in 10 mils final volume. And also this is a two-step serial dilution because it basically involves two steps. So the first step has to do the dilution of the 10 molar to the 5 molar, and the second step has to do with the dilution of the 5 molar to the final concentration that is required, which is the 0.05 molar. So let's start with the first step. So we are going to use the equation C1V1 equals C2V2. So where the C1 is the stock concentration, which is the 10 molar, the C2 is the final concentration that we will prepare here, which is the 5 molar. The V2 is the final volume from the question, and V1 happens to be the amount or the volume of C1 needed to prepare the final concentration C2 in a final volume of 10 mils. So what you do is to make V1 the subject. So making V1 the subject from this equation, we have V1 equals C2V2 all divided by C1. And substituting these values into this equation, we have V1 to be equal to 5 mils for the first step. Now let's look at the second step. So for the second step, we also use the equation C1V1 equals C2V2, where C1 in this case is 5 molar, and V2, which is 10 mils, and C2 is 0.05 molar over here. Also, V1 is also the volume of or the mils of the 5 molar needed to prepare the final concentration of 0.05 molar in a final volume of 10 mils. So making V1 the subject from the equation C1V1 equals C2V2, we have V1 to be C2V2 all divided by C1. And substituting these values into this equation, we have V1 to be equal to 0.1 mils. So what it means is that to prepare the 0.05 molar from our stock standard solution of 10 molar from the example 2 that we just saw, we will first have to pick 5 mils of our stock solution of the 10 molar concentration and add it to 5 mils of distilled water to prepare the 5 molar solution over here. And it's like also to prepare the final concentration of the 0.05 molar solution, we will pick 0.1 mil of the 5 molar solution and add it to 9.9 mils of water at seen over here. So this is just a simplified explanation to the example 2. So from this simplified diagram over here, what it means is that to prepare 5 molar from the 10 molar standard solution and also to prepare 0.05 molar solution. So what we have to do is that to prepare this molar from the standard solution, we pick 5 mils of the 10 molar solution and add it to 5 ml of distilled water. And to prepare the 0.05 molar solution from the 5 molar, we pick 0.2 mils of our 5 molar solution and add it to 9.8 mils of distilled water. So now let's look at the reasons for serial dilutions. So what we have to notice is that the general purpose for serial dilution is to 1. Dilute a highly concentrated solution to create a less concentrated solution, and 2 is to avoid transferring very small volumes to make a highly diluted solutions or less concentrated solutions. And one major problem with serial dilution is that one error or contamination issue in one of the steps involved in the process can be amplified down the series of dilution. So this is one key problem with serial dilution. So once there's a mistake in one of the steps, that error runs through all your steps. So now let's look at some sources of errors in serial dilution. So wrong calculations, inaccurate pipetting of volumes, use of volumetrics, and improper cleaning of glasswares are all sources of error when performing serial dilution. Also, what we have to note is that inaccurate pipetting or pipetting errors can occur due to incorrect pipetting techniques. One, so using pipette that is not calibrated correctly, or using the wrong size pipette for the volume being measured. So let's now look at some lab glasswares and their uses in serial dilution. One is the first has to do with the beaker. So the beaker is used to hold liquid samples in the lab. The next is the Elemea or the conical flask. And this glassware is used to store samples and used to mix solutions to carry out chemical reactions and titrations. So the next is the graduated or the measuring cylinder. So what you have to notice is that the measuring cylinder is specifically made for measuring liquid volumes, as they have a higher accuracy for measuring volumes. So the next is the volumetric flask, and the volumetric flask is used in preparing accurate volumes of solutions and reagents in the laboratory. The next is the pipette. So the pipette is used to measure volumes and dispense them, as they also have higher accuracy for measuring liquids. And the test tubes It's used to hold mix and sometimes heat chemicals. The next is the boiling test tube. So the boiling test tube is purposely designed for heating chemicals and other solutions or reagents in the laboratory. So the next is the burette, and the burette is used to dispense volumes of liquids in a chemical reaction. And the last glassware that we are going to look at is the watch glass. And the watch glass is used when the volume of liquid is very small but needs a larger surface area to work with. And it is also good for crystallization and evaporation processes in the laboratory. So as we can see, the watch glass has a large surface area to work with. So now let's move on and look at titration. So we'll start by looking at what titration is. So when we talk of titration, it's a quantitative analytical method used to determine the concentration of a solution using a second solution of a known concentration, so which is a standard solution. And let us also look at an acid-base titration. So when we talk of an acid-base titration, it is a titration method used to determine the concentration either of an acid by neutralizing it with a known basic concentration, or a base by neutralizing it with a known acid concentration. So this is a setup for our acid-base titration over here. So this is our rotor stand or the ring stand. This is our burette, and this is our Erlenmeyer flask or conical flask. So what you also have to notice that the burette always contains our standard solution or the standardized solution, which can either be a base or an acid. And the Erlenmeyer flask also contains the sample to be titrated with the indicator. So the keynote is that when performing a titration, the solution in the burette is usually a standard solution, either an acid or a base. So let's look at some terms in titrations. The first has to do with a standard solution or titrant. So when we talk of a titrant, so it is the solution with a known concentration, and this solution can either be an acid or a base in a titration. So the next is the analyte or the titrant. So the analyte is the solution with an unknown concentration, and this concentration can be determined from the titration, and the analyte can either be an acid or a base in an acid-base titration. The next is the equivalence point. So when we talk of equivalence point, it is the point at which equal moles of both the titrant and the titrant are being used in the titration. And the end point is the point at which the indicator changes color in the titration. And when we talk of indicators, so indicators are substances that change color when they are added to acidic or alkaline solution. Example of some indicators are litmus paper, methyl orange, and phenolphthalein. So let's look at some errors in titration. So let's start by defining what titration error is. So when we talk of titration error, it is defined as the difference in volumes between the observed endpoint and the true equivalence point in a titration. So the difference between the volumes at the end point, and the true equivalent point is what is termed as the titration error. So now let's look at some sources of error in titration. So the first source of error happens to be human error. So when we talk of human error, so these errors occur due to lack of experience, improper training, and carelessness on the part of the analyst. So common examples of human errors include misreading of the Biret scale, wrong calculations, adding too much or too little indicator, failing to detect the endpoint accurately, improper use of volumetrics, inaccurate pipetting, and improper cleaning of glassware. So these are some of the human errors that normally occurs in titration. So the next is the equipment error. And this can occur due to various reasons such as calibration issues, mechanical defects, or contaminations of the equipment. For instance, if the burette is not calibrated well, it can lead to inaccurate volume measurement, resulting in incorrect titration result. Also, leaking burette can cause loss in volume of the titrant, hence affecting the result. So the next sources of error in titration is the procedural error, and these errors occur due to issues related to titration procedure itself, such as improper stirring, inadequate rinsing of the equipment or glassware when in use. Example, when transferring two different solutions using the same pipette and not rinsing the pipette with distilled water in between. And finally, failure to standardize the titrant. So the next is the chemical error. So chemical errors arise due to issues related to the chemicals used in the titration. Examples: impurities in the titrant or the samples can affect the accuracy of the titration result. And similarly, if the solution being titrated is not properly mixed, it can lead to inconsistent results. So now let's look at acid-base indicator. So what is an acid-base indicator? An acid-base indicator is either a weak acid or a weak base that exhibits a color change as the concentration of the hydrogen ion or the hydroxide ions changes in an aqueous solution. So they are used in titration to identify the endpoint of an acid-base reaction, and they are also used to gauge pH values. Now let's look at how an acid-base indicator works in titration. So first of all, if the indicator is a weak acid, the acid and its conjugate base will display different colors. And if the indicator is a weak base, the base and its conjugate acid will also display different colors. Example, for a weak acid indicator like phenolphthalein, with the general formula of this, equilibrium is reached in the solution according to the chemical equation as seen over here. So where this is the acid and its conjugate base is this. So what we have to notice is that when the pH is low, the concentration of the hydronium ion is high and equilibrium shifts towards the left, producing the color A, which happens to be in an acidic medium. So the color for for the phenolphthalein in an acidic medium is colorless. And also at high pH, which is in an alkaline medium, the concentration of the hydrozonium ion is low. So equilibrium shift towards the right side of the equation, and the color B is displayed in an alkaline medium. So what we also have to note is that the equilibrium constant for this reaction can be determined using the equation given as this. So where this is the indicator dissociation constant, and this is the concentration or the acid concentration, and this is the concentration of the acid conjugate base. Thank you.